This class is about scientific computing, which is, or at least I think it is, a piece of a much bigger picture, which sometimes goes under the name computational science and engineering. So, computational science and engineering is about doing big science with computers, putting together analysis, mathematical analysis on the one hand, and computation on the other hand, with some interesting application that somebody else in the world cares about. So there's a lot of potential applications. Essentially, anything that uses continuous mathematics and interacts with a computer falls into this picture. Now, the goal of doing computing, if you're interested in computational science and engineering, is not to crunch out a bunch of numbers. I mean, that's one of the effects, but that's not really the goal. The real purpose is to gain insight, maybe to figure out quantitative parameters in your design. And a part of this is going to be computation, and a part of it is really going to be related to the specifics of the application you're dealing with. And in particular, this means that you're probably going to be computing something which is a model of how the real world works. Models are not right. Uh, and you will have to deal as a computer with the fact that models are not right. And in some cases, that means that the answers you give will be wrong because the model you set up was wrong. And in some cases, that means that you can say, hey, wait a second, this model is wrong and inconvenient. There's an equally useful wrong model, which is much more convenient to compute with. And because I know the properties of how numerical computations work, I know that I prefer that model. So, really, when we're thinking about numerical computing, we want to keep that application framework in the back of our head. Our goal is something that's fast enough and robust enough and general enough to be useful for applications. And how we get to fast enough and robust enough and general enough is a matter of mathematics and computer science. That's really what this class is about. But how we define what fast enough is and define what robust enough is, that's defined by the application. And really, I think one of the exciting things about this area is the fact that as somebody who practices scientific computing, I do get to talk to people who are involved in different applications and hear about the types of things that they do and maybe push it along a little bit. Now, you might be thinking when I say applications that I'm talking about climate modeling or talking about building MEMS, which certainly is one of the things I do. But applications are really everywhere. And I want to drive this home in particular if you happen to be a computer science student. Because despite the fact that a lot of computer science is about discrete mathematics, there's applications of continuous mathematics everywhere in computer science as well. So the classic places where computational science and engineering appears are big science applications like climate modeling or fusion modeling or things like that. Big engineering applications, computer aided design tools for building circuits or building buildings or building airplanes. All of those things involve computers in the design process these days. Control systems, you probably have computers that are doing some computation with continuous mathematics in your car, in your iPod, in anything that's interacting with you in a physical way. Computational biology is a hot area if you want to understand either the large scale statistics of massive volumes of genomic data, or if you want to understand things like protein folding and try to model that, you probably want to use a computer. Computational finance, we've all heard an enormous amount about, particularly since 2008. If you're in computer science, you might be interested in machine learning. Maybe you're interested in graphics and game physics and movie special effects. Maybe you think that biomedical imaging is the wave of the future. Maybe you're interested in classic information retrieval. say, working at Google one day. The Google eigenvalue problem is probably the world's largest and most successful eigenvalue problem. Or you might be interested in systems. I just finished reading a thesis not very long ago about optimizing certain aspects of peer-to-peer networks. It was a systems thesis, but at the heart of it, there was an optimization problem, which is why I was on the committee. And so on. There's more applications, but there's not more room on this slide, and that's probably a good thing. So this class, although it fits within the larger framework of computational science and engineering, really is going to drill in on the computational aspect of it. We don't have a common physics background to draw on. Most of you have had, I hope, some calculus and linear algebra, but you haven't had an enormous amount of, say, real analysis and complex analysis and stuff like that. So the computation is really where we're focusing. And our goal in the class is to learn enough about the computation and about the analysis to be able to use numerical methods wisely when they come up. Really, think of numerical methods as being algorithms for continuous problems. And this is the same picture that you see when you're taking an algorithms course that deals with, say, sorting and searching algorithms. You're not going to write a new version of quick sort or bubble sort or whatever your favorite sort today happens to be. But you learn about the properties of those algorithms because you might want to use those ideas yourself. You may, on occasion, want to implement those ideas in a specialized way, and you want to be able to make informed decisions about what type of sorting algorithm is appropriate. The same thing is true with numerical methods. You have to understand enough about the basics to be able to understand which tool is the appropriate one to use. Right? So that's the computational part. What about applications and analysis? Well, we need the applications to be able to ask meaningful questions that tell us what properties we can expect that we can exploit with our numerical methods. And we need the analysis to understand what properties we should look for. So, while we're going to be focusing on numerical methods, these continuous problem algorithms, the analysis and the applications still do matter, right? So the ideal case is we're designing fast, accurate, robust methods for cool problems that come from the real world in some sense. Now, the real world is complicated. It doesn't always fit very well into a 50-minute lecture or into a problem set. So some of the problems that we do in this class will be a little bit contrived, but it does come up in the real world, and that's why I enjoy this. The first half of this class is mostly going to be about basics and numerical linear algebra. So that's up to spring break. When I say numerical linear algebra, think solving linear systems, solving least squares problems, iterative methods for solving really big linear systems, solving eigenvalue problems, and applications of all of those things. We're also going to talk about solving nonlinear equations, both in one dimension, that comes pretty early, and systems of nonlinear equations, that comes after numerical linear algebra because it's hard to talk about without the language of numerical linear algebra. So that's the first half of the class before spring break. After spring break, we're going to be talking about what I think of as numerical calculus. So interpolation, function approximation. You can think of those as being the analogs of talking about Taylor series, if you like. Taylor series is going to come up a lot in this class. Differentiation, quadrature, which means the computation of definite integrals numerically, and the solution of ordinary differential equations numerically, right? So it's okay if you haven't had a linear algebra class. You should know a little bit of linear algebra, if only from taking a basic multivariable calculus class. I will assume that you remember some calculus. If you don't, you'll need to brush up as we go along. I'm also going to assume that you're familiar with MATLAB. If you're not familiar with MATLAB, it's not that difficult to pick up. There's a transition course which is offered every semester. It's offered this semester as well. So if you're familiar with Java, this introduces you to MATLAB as somebody who knows about this other programming language. Alternatively, you can pick up the book by Cleve Moeller. There's a link from the web page. And the first chapter of that has a pretty good introduction to MATLAB, as well as some pointers to more advanced MATLAB features that might be of interest to you. You can go to my webpage to get a detailed syllabus for the class and more. If you're watching this video, you've probably already seen that because very likely you're coming to this from the link on my webpage. If not, though, there it is. And let's move on to error analysis.